Now, since we just followed the ventral visual stream into the temporal lobe, let's go back and see where the dorsal stream leads us. That's right into the parietal lobe. The parietal lobe does some pretty high-level processing, taking information from many different senses to make sense of our environment and determine where we are in space with relation to what's around us. This area of the brain is actually about where you'd expect such a computation to take place, if you look at what's going on around it. In the next video, we'll talk about the motor strip and the frontal lobe, where voluntary movement is planned out. It's important for you to know where you are in space to make such plans, and hence, the parietal lobe comes just before these areas in terms of visual processing. When you want to interact with a moving object, like catching a ball, you want to integrate moving objects into this picture, and for that, the parietal lobe is getting direct input from the dorsal visual stream, which, as we just said in the last video, processes visual motion. The parietal lobe is situated very close to the auditory cortex, so it can integrate that auditory source localization information, which we discussed in the last video, in order to determine where objects are around us that might not be visible in our visual field. In the parietal lobe, we also find the somatosensory strip. This is the part of the brain that manages our sensation of touch. Again, something very useful for knowing what's around us and where we are in space. It suddenly becomes very clear why this area of the brain in particular handles the integration of data processing from across the brain, and why it's situated at the very center of our neocortex. Let's talk some more about that somatosensory strip that I just mentioned. It's also known as the somatosensory cortex, and it's really interesting because its processing is localized, not global. Now, what I mean by that is that the neurons that respond to touch in your hand are all bunched together in the brain, rather than being distributed over a large region, tangling up with other neurons of different tasks. What's really cool about this is that this creates this nice little map of the human body along the somatosensory strip, called the somatosensory map, and you actually end up finding a similar map of the body in the cerebellum. Now, as you surely know, not all body parts are equal, and some are more sensitive than others. And this, too, is represented in somatosensory cortex. Areas like our hands and lips, which are very sensitive, take over lots of cortical real estate, and other areas like our backs and elbows take up considerably less cortex, and therefore less neurons. If you take the relative sizes of these different body parts as they're represented in the somatosensory strip, you can create a distorted model of a human, where bigger body parts represent areas with more devoted cortical real estate, which are therefore more sensitive and precise to touch, and smaller ones less so. We call such a model a homunculus. Now, as I said at the beginning of the video, the parietal lobe is responsible for mapping out where we are in space, and so if you lesion it, you find some very interesting phenomena. Individuals with strokes or other damage to one half of the parietal lobe can experience hemispatial neglect. Now, if we break down this word, you look at hemi and you see half, and it's half of a spatial field, and they neglect that half. And that's exactly what you see. These hemispatial neglect patients completely ignore one side of their body. Everything that's there simply doesn't exist for them. The side that they ignore is the opposite side that the lesion occurs in, so damage to the left parietal lobe causes right hemispatial neglect, and damage to the right similarly knocks out the left field. If you watch the first neuroanatomy video in this series, you'll know that you can rephrase this as parietal lobe lesions cause contralateral hemispatial neglect. It's interesting to note that hemispatial neglect occurs much more frequently and severely in the left visual hemisphere, meaning that it was caused by damage to the right side of the parietal lobe. This is thought to be because a fair amount of the left side of the brain is devoted to language, and so when the right side of the parietal lobe gets knocked out, the left is already overloaded with so much processing that it can't take over the extra duties of the right side. However, when the left parietal lobe is damaged, the right parietal lobe is often able to free up some of its connections and take over the computations that used to be processed in the left side, meaning that the patient will quickly recover from the hemispatial neglect. As you might expect, if you show a hemispatial neglect patient a picture and ask them to draw it, they will only draw half of the picture, leaving out the half that's in their neglected field. But this isn't a visual issue. If you ask them to draw a clock, for example, they'll put all 12 numbers on it, but they'll scrunch them all onto one side. Perhaps even better evidence that the problem is not visual is this next example. If you tell a hemispatial neglect patient to imagine that they're at a well-known place, like the mall or school, and ask them what they see, they'll rattle off a list of what is on their good side. Let's say they neglected the left side, so they list everything on the right side of the mall. But now, you ask them to walk to the other end and turn around, and then tell us what they see. And now, they report everything that was on the left side, because they now picture it being on their right. There's no visual input for this task. It's all imagined, and yet they still never perceive anything on the neglected side of the body.